Today, the quadratic skill that we're going to talk about is simplifying square roots. This is something that you have likely done before, but we're going to practice it again because it usually needs some extra practice. So in simplifying square roots, if we have two separate square roots multiplied together, what we're going to do is start by multiplying the numbers together and putting it all underneath one square root. Then my directions here suggest making a factor tree until you have all prime numbers at the end of your branches. I'm going to show a little bit different of a way of thinking about that, but if the way that I instruct the whole class in doesn't work, then I will privately show you what I mean by a factor tree. So for this problem, first thing we would want to do is multiply, go back to that. Multiply the 24 times 8 and put that underneath one square root. It's 192? Alright, so I get square root of 192. Then what we want to do is think about square roots that would divide into there. Perfect squares that are going to divide into there. So remember from yesterday we said perfect squares like 1. Well, that's not really special. Everything divides by 1. 4, 9, 16, 25, 36, 49, 64, 81, 100. And these are some of our perfect squares. We want to look for the biggest one of these that divides into there. So I'm going to say, well, even maybe 4 goes into it. So I could do 192 divided by 4, and I get 48. So then what I'm going to break this down into is the square root of 4 and the square root of 48. Because 4 times 48 would give us that number. Now 48 is still pretty big. So I want to make sure that that doesn't break down anymore. With a 4 and an 8 in there, I kind of feel like it probably divides by 4. So I'm going to divide that by 4 as well. So then I get 4, and 48 is 4 times 12. Well, 12 I know still divides by 4. So I can now break that down into the 4 and the 4 that were already there, and 12 becomes 4 times 3. So each time what we're doing is just breaking down a number more so that one of the numbers is a perfect square. So first I said 192 is 4 times 48. Then I took that 48 and I turned it into a 4 times 12. Then I took the 12 and I turned it into a 4 times 3. And I can't break these down anymore. Now some of these numbers I can take square roots of. The square root of 4 is 2. So this is going to become 2 times 2 times 2. Square root of 3 I can't take. It's not a pretty number. So that leaves me with 8 square roots of 3. 2 times 2 times 2 is 8. What that means is, from the beginning, if I had kind of kept guessing checking and said, yeah, 4 goes in there, but maybe a bigger number goes in there, right from the get-go, I could have done 192 divided by 64, and it's 64 times 3, and that would have gotten me to 8 square roots of 3 right away. But if you don't pick the biggest one, you just keep on breaking it down as much as possible. So we're going to start by multiplying them together and putting them all underneath one square root. So that gives me the square root of 24. Then I want to think about the biggest perfect square that divides in here. So 4 goes in there, for sure. But I want to think, are there any bigger ones? 9 does not go in there. 16 does not go in there. 25 is now bigger than this, so that doesn't go in there. So 4 must be the best bet. 4 times 6. And then take a square root when you can. The square root of 4 is 2. The 6 we can't do. A lot of times students are like, that doesn't look any more simple because it's still square roots and it's still two things. The idea is that we want the smallest numbers possible underneath the square root. This comes back to really the idea where this started in importance was before we had calculators that we could easily type square roots into, and we had to actually think about calculating square roots by hand or using tables of square root values. It was a lot easier if we had small numbers underneath our square roots. So 72, I want to think about what divides into 72. So, I don't know, maybe 4 goes in there, so I could try that. 72 divided by 4, I get 18. So that's an option. We could do that. But maybe something bigger goes into 72. 9 goes into 72, 9 times 8. Maybe something even bigger. So 9, 16 does not divide in there. 25 doesn't go in there. 36 does though. So I could break this down to 36 times 2.
But wouldn't you want both of them to be small? You just want the second one.
We want the one that's not a perfect square to be as small as possible.
Okay.
We want the perfect square to be as big as possible. So that's 6 square roots of 2. If you had stopped earlier and not gone all the way up to 36, this problem would still totally work out. So if you said 72 divides by 4, I would do then, it can work, 4 times 18. But then we would need to break down 18. 18 is 9 times 2. And then we could say that it's 2 times 3 and square root of 2, and we still get the same answer, 6 square root of 2. So you don't have to pick the biggest number, it's just quicker if you do. If you don't pick the biggest number, you just keep on breaking it down until you can't break it down anymore.
They'll always be the same.
It'll always end up at the same answer as long as you do all your divisions correctly. 108. So I'm thinking about a big square root that goes into 108. I can try dividing by 4. That's not very big, but it works. I got 27. 27 I know divides by 9. So 108 must divide by 9 as well. I get 12. That I think should still have some stuff that goes in it. So maybe 108 divides by 36.
Yeah.
And it does. It's 36 times 3. So then I get 6 square roots of 3. Again, if you don't pick the best one right off the bat, it's fine. So if I started by doing the 108 and dividing it up by 4, when I divided by 4, I got 27. And then I would just want to break 27 down and say that it's 9 times 3. Which would give me 2 times 3 to the square root of 3, which is still 6 square roots of 3.
Well, how come you didn't do like 54 times 2?
Because 54 and 2 are not perfect squares. So we want at least one of the numbers to be square rootable. And this one we've got a number outside. It's just going to hang out outside, but I'm going to multiply the inside stuff together. So 38 times 72 gives me 2736. A very large number.
Did you say 27?
72 times 38 is 27. Oh yeah, I did say 27. And then I wrote 37. Thank you. Alright, so now I want to think about some stuff that goes into this. We could try to start big and say, I don't know, maybe 144 goes into here. And it does. So that was a good first guess. So it is 144 times 19. $19 is a perfect prime number, so I can't break that down anymore. There's nothing that divides into 19, not any perfect squares, but not anything that divides into 19, so that doesn't go anywhere. The square root of 144 is what? 12. So then I get 24 square roots of 19. If you hadn't aimed as big for 144 and you just divided up by like 4, you would just keep on dividing as long as you can divide.
Yeah. 2 square root of 6 square root of 19, because I didn't do like that as big of a number.
Okay.
So
Um,
that's 6
What did you divide that first number by?
By 36.
2736 divided by 36.
76.
It's 76. Okay. So then we'd have 36 and 76, and then we'd want to divide down 76 and say what can go into 76, and that divides by 4. And so then I would get a 2, a 6, a 2, and the 19, and 262 multiplies to make 24.
Okay, I just.
I tried to find out.
So you always have to put the number you divide by and the answer you got in there. Like
Yes.
the
Yep.
square root.
Yep. When you divide it up, both of them need to still be there under square roots. Alright, when we have a fraction, the first thing we want to do is simplify the fraction if it's possible, because that gives us smaller numbers to work with. So we want to try to reduce our fraction if we can. 45 and 32 do not have anything that divide out of them, so this one cannot be reduced. But that is a good thing to do first, especially I know there's at least one homework problem that it will make it a whole lot easier if you reduce the fraction before starting. So, no. So just on all of them, make sure you try to reduce your fractions. Then what we're going to do is separate it so that we have the square root of the top and the square root of the bottom individually. So I'm going to separate this into the square root of 45 over the square root of 32. Then we want to simplify those square roots, if possible. Sometimes it won't be, sometimes it will be. So just like we were doing, we want to do that on both the top and the bottom. So what goes into 45? 9. What goes into 32? 8 and 4. Okay, think bigger. 16. 16 and 2. 8 and 4 will work. You just have a little bit more work to do on the 8 there. So if we start at 16 and 2, then we don't have to break it down anymore. So this is going to be 3 square roots of 5 over 4 square roots of 2. So separate them so they're two individual ones. Simplify them both the way that we did the first problems. Then it is considered inappropriate to leave a square root on the bottom of a fraction. Again, the reason why this habit started was back to when we didn't have calculators to do our arithmetic easily for us. What we would have to do is look up square roots in a table. So I would simplify the problem down to here, and I would look up what is the square root of 5, and it would tell me the long decimal. Then I would have to, by hand, multiply that by 3. Then I would, and that's still a long decimal, right? So then I'd have to look up what is the square root of 2. That's a long decimal. I would have to, by hand, multiply that by 4, which is still long decimal, and then by hand do long decimal divided by long decimal. That doesn't seem like a good thing. So the goal was, if we can at least make the bottom of the fraction clean, that'll make the division easier. Okay? So that's why this habit started, and then it just continues to be a habit in math that is considered inappropriate to leave a square root on the bottom of a fraction, that it's not simplified when that happens. So the way we do this is we take whatever the square root on the bottom is, because we're only trying to fix the bottom, and we're going to multiply the top and the bottom by that square root that's on the bottom. So since the bottom is the square root of 2, I'm going to multiply both the top and the bottom by the square root of 2. Why is that a legal thing to do?
It cancels it out.
Because it really cancels out, right? Square root of 2 over square root of 2 is really just 1. So I'm really only multiplying this problem by 1, which is always okay to do, because multiplying by 1 doesn't change a value. When we multiply together numbers that are underneath the square roots together, and stuff that's outside stays outside. So on the top I get 3 square root of 10. On the bottom I get 4 square root of 4. What is the square root of 4? 2. So this is really just 2. So on the bottom then I have 8.
Couldn't you just square it?
If you square it, that changes its value. We want it to be exactly the same number. Just like when you reduce a fraction from like 3/6 to a half, it's exactly the same value, it just looks different. That's what we're trying to do here, is make sure that it stays exactly the same value. Like if we would type into the calculator, and that's one way you can check your answers. You can't do this on the calculator, but you can check it on the calculator by typing the original problem in and then typing your answer in, and they should be exactly the same decimal. Okay? And if they're not, then something went wrong along the way. This process is called rationalizing. It's making the bottom of the fraction into just an integer number instead of a decimal number. Alright, so first thing we want to check for is, does it reduce? 11 does not go into 144, so it does not reduce. So then we separate and give the top and the bottom each their own square root. Then we want to deal with the top and the bottom individually, simplifying them if possible. What's the square root of 144? 12. Square root of 11, does that break down at all? No, 11's a prime number, so that can't break down. But we are not allowed to leave a square root on the bottom of a fraction. So we are going to multiply it by itself and multiply the top by the same thing. So we're really just multiplying by 1. So on the top, 12 is outside and will stay outside, 11 is inside and will stay inside. Square root of 11 times square root of 11 is square root of 121, which is 11. So I get 12 square roots of 11 over 11. The 11 inside and the 11 outside does not cancel or reduce. You cannot cancel numbers that are in different locations. If something is inside, it does not cancel with something outside. If you have two things that are outside and they reduce, you can do that. If you have two things that are inside and they reduce, you can do that. But you cannot reduce something outside with something inside. Okay? Questions? All right, 7/8 does not reduce, so we separate it. Simplify each root individually. Does 7 break down? No, 7 is prime, so it can't break down. Does 8 break down? 4 and 2. The square root of 4 is 2. But we're still left with a square root on the bottom. We're not allowed to leave a square root on the bottom for our final answer, so we are going to multiply by the square root that's on the bottom. We don't have to multiply by anything else. So we don't have to multiply by the 2 in the front on the bottom because that's not a problem. We only need to fix the problem, and the problem is the square root. So we're going to multiply by the square root of 2. Multiply by the same thing on the top so that we're really only multiplying by 1. On the top, that gives us the square root of 14. On the bottom, square root of 2 times square root of 2 gives square root of 4, which is 2. So I really have then on the bottom a 2 and a 2, which we multiply, don't add, we multiply those, and that gives us a 4. In this case, multiplying and adding are the same thing, but we want to multiply those. Again, you cannot reduce the 14 and the 4. Students get tempted and try to divide it out and have it be 7 over 2. We can't do that because one is inside and one is outside. We can't reduce if they are in different locations. Questions? $36 and 72, those are both kind of big numbers. Does this fraction reduce? Yes. It is 1/2, and that will make your life easier if you reduce instead of dealing with big numbers. Okay, so check as your first step to see if the original fraction reduces. And if it does, reduce it. Then separate it. Square root of 1 is just 1. Square root of 2 doesn't really do anything, but we're not allowed to leave it on the bottom. So I'm going to multiply by square root of 2 over square root of 2. on the top, that gives me square root of 2. On the bottom, that gives me
2.
square root of 4, which is 2. When you multiply a square root by itself, you just get whatever was underneath. Questions on that one? $99 and $242, pretty big numbers. Do they reduce? $242 does not divide by 3 or 9. They both divide by 11. They both divide by 11, which leaves 9 over 121. No, 22. Divided by 2 would be 121. Divide both by 11, and we get 9 over 22.
Is that our answer?
It's still a square root of a fraction, so that's not our answer yet, but that's our first step is we want to reduce it. Then we split it. Square root of 9 is 3. Square root of 22, do any perfect squares divide into 22? No. 22 is just 2 times 11, and neither one of those are perfect squares, so there's nothing we can do to break down that 22. But we're not allowed to leave it on the bottom. So I multiply by it on both the top and the bottom, which gives me what on the top? 3 square root of 22. The 3 is outside, so it stays outside. Square root of 22 is inside, it stays inside. And on the bottom, multiplying a square root by itself, we could actually multiply that together and then take a square root, but multiplying a square root by itself does what? This cancels and gives you whatever was underneath. Your homework tonight is from 5.3. Please notice it is multiples of 3.